Thanks for the introduction. Yes, my name is Sven Luther, and I'm a junior scientist in the ReMade project from the Smart Science cluster, where I'm responsible for the high magnetic fields. And today I want to talk about materials characterization in highest magnetic fields. And I'm working at the High Magnetic Field Laboratory in Dresden, which is here in east of Germany. And Dresden High Field Lab, short HLD, is part institute of the Helmholtz-Zentrum Dresden-Orsendorf, short HZDR, which is here a bit outside of the Dresden city center. And here you can see this is our campus, where we have here the main entrance, and then the High Field Lab is located here. And in our whole HZDR campus, we have almost 1,500 employees working in different institutes, for example, the High Field Lab, the radiopharmaceutical cancer research or fluid dynamics, but also other partners working in the ReMade project, for example, the Ion Beam Center, which is located here, and also the positron facility P-Albe, which is part of the radiation physics, just based here behind the High Field Lab. So this is the outline of my talk. So first of all, I want to show how we can actually generate highest magnetic fields. And here I want to show you the journey from static to pulsed magnetic fields. And the second part, I want to present the EMFL facilities participating in the ReMade project, which is first the High Field Lab here in Dresden with its pulse field magnets, and the High Field Magnet Laboratory in Nijmegen in the Netherlands with the static fields. And then I want to show the experimental techniques we are offering within this ReMade project. So I want to give a rough overview about our techniques. Then I want to show some selected techniques, how we can actually characterize materials in highest magnetic fields. But first of all, I want to start what are actually the magnetic fields in our nature. So we have here at extremely low fields, the biological magnetic fields in the range of 10 to minus 15 Tesla, which is, for example, generated from our brain, up to 10 to minus 9 Tesla. Then the field in our Milky Way, or in general field in galaxies, are in a range of 0.5 nanotesla. And in the range from 10 to minus 12 to 10 to minus 3 Tesla, we have technical stray fields, which come, for example, from trams, buses, mobile phones, computer, and so on, which is called the urban noise. The Earth's magnetic field is in the range of 20 to 50 microtesla. And the surface of magnets is here in the range of below 1 Tesla. If we go to the internal fields of magnets, we come here in this range up to 10 to the power of 3 Tesla. The highest magnetic fields in nature are here neutron stars in the range of 10 to 8 Tesla. And the field range I want to present in this talk is here from 1 to roughly 10 to 2 or 10 to 3 Tesla. So first of all, I want to show how we can generate highest magnetic fields. So I show here the field strength depending on the time scale. So if we start with permanent or electromagnets, they can create commercially magnetic fields up to 2 Tesla, and they are operating on an infinite time scale. If you want to go to higher magnetic fields, we have to use superconducting magnets. Commercially, we can reach here up to 22 Tesla, but there's also some effort to create all superconducting magnets up to 32 Tesla. And as long as we cool down these superconductors with liquid helium, we can also operate these on an infinite time scale. If we want to go to way higher magnetic fields, we have to use resistive so-called bitter coil magnets. And here we can create magnetic fields up to 42 Tesla, but they can only operate in a time scale from minutes up to several hours. If we want to go further beyond these 42 Tesla, we have to use pulse field coils, and they can create magnetic fields up to 100 Tesla, but they are operating on a time scale from milliseconds up to seconds. For much higher fields above these 100 Tesla, we have to use so-called destructive or semi-destructive single-turn coils, and they can create magnetic fields above 100 Tesla, but here we have a time scale of microseconds. In my presentation, I want to mainly focus on these pulsed and bitter coil magnets. So first of all, I want to start with the static magnetic fields from the superconducting magnets I already showed. So this is, for example, such a solenoid, a superconducting magnet. And as I mentioned, this one has to be cooled down by liquid helium, which is in a temperature range of 4.2 Kelvin. So this magnet has to sit inside such a cryostat here. And as long as you fill every, let's say, once a week with liquid helium, you can operate this magnet as long as you want. But these superconducting magnets are not only for scientific research, they have also medical applications. For example, this MRT scanner, which you can see here, which has actually also a superconducting magnet inside, but with a much wider bore to fit a human inside, and they are operating usually on a field scale of 1 up to 3 Tesla maximum. And if you want to go above these 22 Tesla, we have to use resistive coils, so-called bitter magnets, and they can create magnetic fields up to 38 Tesla. But they need lots of power, so they need a supply of up to 22 megawatt of power supply. If you combine such a bitter magnet together with a superconducting magnet, you can create a hybrid coil, and here the world record lies at 45 Tesla of highest magnetic fields generated. But this one has extremely high cost, so it's about $14.4 million and also needs lots of power of 33 megawatt. So these bitter magnets, they are consisting of so-called bitter plates, which you can see here. So this is just a copper plate, and this has a diameter hole of roughly 10 centimeters. And this is the bore of the magnet here in the range of, let's say, 5 centimeters, where then also has to fit inside our cryostat and our probe and our sample. And as you can see here, this plate has lots of holes inside, because if you apply these high currents, they are also heating up a lot. So you need a certain water cooling for these plates. And here we have 140 liters of water. So let's say 1 bathtub per second running through these plates to cool them down. And these plates are arranged in such a helical format, where in between you have some insulating layers. And you can see this is the cross-section of such a resistive magnet. So you have the electrical power supply to run the magnet to create these high magnetic fields. And then you have the water supply to cool down this magnet. So we have cool water of below 10 degrees Celsius going inside the magnet, and outside of the magnet, we have the water of 40 degrees Celsius to cool down our magnet inside. And this is how such a magnet would look inside the lab. So here you have this big tank where the magnet sits inside, and then the water is running through the magnet to cool it down. Then on top we have here the cryostat and people who is inserting the probe inside the magnet. And if we want to go to much higher fields, we have to use the pulsed fields, and there we have different technological challenges. So as maybe some of you know, we have Lorentz forces acting on the wires, which are perpendicular to the velocity of the electrons and to the magnetic field. So we have from these forces a certain magnetic pressure, which goes straight to the magnetic field, which means if you double the magnetic field, you have already 4 times the pressure acting on the wires. And at 100 Tesla, we have already 4 gigapascal. And you can imagine this, you have a wire of 1.8 millimeter diameter, where at the end you have a weight of 1,000 kilogram. That's the pressure acting on this wire. And then they made also some experiments to show how would this act if you just change the current. So at 9 kiloamp, you see the coil is still alive. But at 10 kiloamps, you can already see how this coil is blown up because these forces are acting to the outside. And if we go to higher currents at 11 kiloamps, you see the whole coil is already fragmented. And to overcome these forces, we have to tame them, because the best high-strength wires apart about 1 gigapascal, which is 10,000 bar. Ambient pressure is roughly at 1 bar. You see there's lots of pressure acting on these wires. And in our workshop, we reinforce them by an insulating fiber, which is called Cylon. And the Cylon withstands a pressure up to 5.5 gigapascal. So you can see here from our workshop how these coils are winded. So you have these copper alloy cables or layers, and in between every layer, we put this Cylon, which you can see here. If we cut off such a coil, you have here these layers of the copper alloy wires, and in between we have these Cylon insulating layers to hold our coil together. And to run these high energies in the Dresden high-field lab, we have the largest capacitor bank worldwide. So you can see this is a sketch of our laboratory. In the front, we have our in-house research with superconducting static fields. And in between, we have our capacitor banks to energize our magnets. And in the back, we have different cells with different pulse width coils creating different magnetic fields, which are energized by our capacitor bank. So this is how our capacitor bank would look from the inside. So here we have the different capacitors, which are energized, and then we let the current flow through our coils to create the high magnetic fields. And here in this capacitor bank, so the total capacitor bank has a maximum energy of 50 megajoule and a maximum voltage of 24 kilovolts, a maximum current of 500 kiloamp, which means we have a maximum power of the whole capacitor bank of 5 kilowatt. And to give you some impressions from our lab, because we are dealing here with really high energies, and it may also happen that the coil fails and fragmentates. That's why during the experiment or during the pulse, no one is allowed to be inside the lab, and we have to close the cell with these heavy doors to fulfill our safety standards. This is how our such a pulse width coil would look like in our workshop, and this is how such a cell would look from the inside where the coil is installed here. To give you an impression, what are actually 50 megajoule of energy? There is this equivalent, you can say 50 megajoule are equivalent to 2.2 kilogram of chocolate, or if you count this in alcohol, you have 9.6 liter of martini. Or if you imagine you have a locomotive of 60 tons running or driving at 150 kilometers per hour, and this one is stopped immediately. These are equivalents to 50 megajoules of energy. So in our labs, we are running different pulse field magnets. The main magnets are these single coils, which can create magnetic fields up to 70 Tesla. So this is how the magnet would look like inside our lab. And then we have our typical pulse field shape. So this is the magnetic field depending on the time. You can see the total pulse is done within just 100 milliseconds, which has a rise time of a few 10 milliseconds, and then we reach the maximum field here. Our record of highest created magnetic field in our lab was in 2016, where we created 95.6 Tesla, and this was done in a so-called double coil. Which you can see here, the sketch. So we have an outer coil, which is creating the typical pulse field shape, which I've already shown before. And on top of this, we have the inner coil given the peak to reach the maximum field of almost 96 Tesla. But in our normal user access, we are running this double coil and fields up to 85 Tesla. So our lab is part of the networked European Magnetic Field Laboratory, EMFL, And in the EMFL, we have 4 different labs, which is first the high field lab in Dresden with its pulse field magnets, and then the high field magnet laboratory in Nijmegen in the Netherlands, having static magnetic fields. And then we have also in France 2 labs, which is another static field lab in Grenoble and another pulse field lab in Toulouse. But only the HFML in Nijmegen and the high field lab in Dresden are part of the ReMade ARI project. If you want to have a look inside of our labs, I can also promote use our online tours. You can just click on these links here for our both labs, and then you can have a online virtual tour. You can go inside the lab. You can see how the cells looks from the inside, how the magnet labs looks from the inside. There are also some videos where we explain what we are doing, how we are measuring, and what are our current research. So you can go here and just have a short tour inside our lab. Now I want to give you some instrumental specification in both our EMFL labs. So at the HLD, we are running various types of pulse field magnets, which can create magnetic fields in maximum up to 95 Tesla, with a pulse duration usually of about 100 milliseconds. In the HFML, we have various types of continuous field magnets, which can create magnetic fields up to 38 Tesla. And to show you, so this is the picture of our sample environment, because from the bore of our magnets, we have a limited sample space. So this is a typical probe which we have, but these always are different for the different techniques, but more or less similar. So you can see here we have several 10 cubic millimeters of sample space. And usually we have sample masses in the range of up to milligrams. We can measure on various types of samples, powders, single crystals, and more. We have a huge temperature range from room temperature or also above down to 500 millikelvin, and our measurements are non-destructive. So in the HLD, we have different available user magnets, which I have listed here. So these different magnets have different maximum magnetic fields, different pulse lengths, and also different bore sizes. So as you can see here, the pulse field shapes, magnetic field over time, so different pulse field duration lengths and different maximum fields. But I also have to say, which is shown here, is only the maximum field. You can also operate these magnets in every field in between. So you can also pulse 5, 10, 20, 30, 40, and so on Tesla. So you don't have to pulse the maximum fields only. In the HMFL, there are also different cells which have different beta magnets with different maximum magnetic fields ranging from 30 Tesla up to 38 Tesla, also with different bore sizes of the magnets. Here, this is a picture from what such a beta magnet cell looked from the inside. So here you can see we have certain electronic equipment to run our experiment. This is the magnet with the water cooling supply, which I already shown before, where on top is the cryostat, where the probe is inserted, and then we have the magnet and the measurement inside here. And here you can see there's a gas handling system to create the temperature inside the cryostat. And then from in our labs, we offer different experimental techniques. So it's different, for example, to beamlines. So we provide the high magnetic fields, and we can measure different experimental techniques in our labs. For example, in the HLD in Dresden, magnetocaloric effect, magnetotransport, magnetization, ultrasound, and many more. And the same is for the static field at the HFML. You can also have a look on the technique catalog at the ReMade website, which is on page 10. The high magnetic fields here, again, it's explained what we're doing in the high magnetic fields, how we are measuring. And then there's the list of our techniques and also short explanations for what is measured in these different techniques. Then if we are running and performing the experiment, For the pulse field lab in Dresden, what is different, for example, to synchrotrons or neutron facilities, we have no beam time. We are counting in pulses. So where we're counting 1 pulse means 1 hour of measurement time, which is 1 unit of access. Because 1 hour is the typical cool down time of our coils, because when we are pulsing, our coil is heated up, and then the coil sits inside of liquid nitrogen to cool it back down back, that we can do our next pulse usually after 1 hour. The measurement time or the measurement operation in our pulse field lab is only during the daytime due to safety reasons, and also only during working days. This can be different for the static field facilities, where it can be also possible that you have to measure overnight because the costs for the electricity are usually lower over the night time. Here you can see this is a picture of our control room on our pulse field facility, because during the measurement we are not allowed to stay inside the cell. So we go to our control room where we can from these computers we can control our experiment. And then the data is recorded usually on an oscilloscope, where the data format is usually voltage over time, which we are recording on the oscilloscope, and this voltage is usually related to a change of, for example, the magnetization, change of the temperature, change of the magnetic field, and many more parameters. And then when we are have done the experiment, the user can get primarily analysis of the data, because we can provide certain software to analyze the different techniques in our lab. And then the user can take home the raw data and also the first analyzed data. And for different techniques, we can also provide the software to further analyze the data when the user is back home. Now I want to go to some experiments where I want to explain in more detail what we are doing. So here I want to focus on the magnetocaloric effect and the magnetization. So for the magnetocaloric effect, we have can have magnetocaloric cooling technologies where we have different elements, alloys, and materials which have a certain magnetocaloric effect or high magnetocaloric effect in different temperatures, where the magnetocaloric effect is a temperature change under adiabatic conditions by applying a magnetic field. This work I'm showing here was mostly done by Tino Dotschall and his colleagues. So at high temperatures, we can have a magnetocaloric cooling cycle. So we can use these elements and alloys to cool down or to create a fridge in a magnetocaloric cooling cycle to cool down, for example, our food or beverages in a normal fridge, but by magnetic cooling. If we go to lower temperatures, we can use these elements and alloys here for liquefaction or magnetic liquefaction of hydrogen, for example. So what I present here is mainly the gadolinium element gadolinium, because this one has a extremely large adiabatic temperature change, and this is told as a benchmark material for the magnetocaloric cooling technology, because this one is also used in the vast majority of the magnetic cooling and heating devices. So in the pulse fields, we have the advantage that we are measuring under adiabatic conditions, which makes our pulse field facility really a good environment to measure the adiabatic temperature change from the magnetocaloric effect. Nevertheless, this gadolinium here is a heavy wear-off element, and this one is classified as a critical element. So you can see here there's a map of different elements and alloys or materials which are performing on different initial temperatures with different adiabatic temperature changes. And these are sketched here in traffic light colors, where red means this one is this element or material is highly critical due to a bad sustainability, bad recyclability, or due to some high costs or political reasons in the mining countries. And green means this material is not critical. You can see here, for example, gadolinium-based compounds, or for example, iron rhodium. These elements are highly critical and they have to be replaced, because also, for example, for the gadolinium in the near future, there's no realistic circular economy for this material. So that's why what could be a path for our research is to find new materials, which, for example, could be rare earth-free, and in the end beneficial for reducing the over-reliance for these certain critical elements or materials. And in the end, to also provide more sustainable and resource-efficient alternatives for magnetocaloric cooling. However, in the following, I will present mainly experiments done on this gadolinium, because this is the benchmark material I want to present. So what is actually the magnetocaloric effect? So this is what we measure here is adiabatic temperature change by application of magnetic fields, because in the pulse fields we are measuring under adiabatic conditions. And you can see this is a diagram of our measurement, where the sample sits here inside the cryostat, where we can perform a high temperature range from 10 to 400 Kelvin. And then in the outside, we have our pulse feed coil, which is cooled by liquid nitrogen, where we can apply magnetic fields in the range from 1 up to 70 Tesla. And in addition to the magnetocaloric effect, we can also do simultaneous measurements of the magnetocaloric effect and also of the strain and the magnetization. Also put an uniaxial load of up to 150 megapascal. And the measurement is done in the following. So you can see a sketch of the sample preparation. So we have the sample sitting here. And here we have our double pickup coils to measure of our external magnetic fields from our pulse feed coil. And the sample preparation is done in the following, that we have this sandwich type preparation, where in between the sandwich we have our thermocouple to measure the temperature change, which is coupled to a reference temperature reference outside of the sample, which is usually a Cernot's thermometer. And then we are recording this on, so the reference temperature is recorded on such a temperature controller, and the change of the sample temperature and also our external field from the pickup coils is recorded on such an oscilloscope. So in red, you can see here usually voltage over time on the oscilloscope. This is the change of the temperature over time. And then from the external field, we usually record dH over dt, so the change of the field over time in black. And by integrating this field over time, we get again in blue our typical pulse feed change, shape field over time. So here I want to present now the measurements of the magnetocaloric effect on this benchmark material gadolinium. So this was measured in high magnetic fields up to 62 Tesla on different initial temperatures. And you can see here, because this material has the Curie temperature or the phase transition at 294 Kelvin. So that's why we have a high magnetocaloric effect at the phase transition of 249 Kelvin, where we have a high temperature change of about up to 60 Kelvin at this temperature. So here I'm showing the adiabatic temperature change depending on the initial temperature measured in different fields. So from so the applied field of 2 Tesla, 5 Tesla, up to 62 Tesla. As you can see here, the highest adiabatic temperature change is usually at the Curie temperature point of 294 Kelvin for this gadolinium material. And so As you can see, the magnetocaloric effect is also always a good tool to measure phase transition in certain materials. In addition, we can not only measure the magnetocaloric effect, we can also measure in parallel also magnetization of the sample. So you can see this is a kind of home-built pickup coil system, which is a compensated pickup coil. So the sandwich sample would sit here inside this coil, which is our magnetization pickup coil, where we again measure a voltage change coming from the change of the magnetization of the sample by applying magnetic fields. And in the end, at this ends here, we have our compensated compensation of the coil of the magnetization to only get, so they compensate the background to only get the magnetization from our sample. And here you can see this is the magnetization of the gadolinium. And these small curve up to 14 Tesla are measured in static fields. And these dash curved are here the measurement at pulse fields. As you can see here at low temperatures, for example at 4 Kelvin, there's no difference between the static and the pulse fields. If I show again this picture here, because at low temperatures, there's no dramatic temperature change or adiabatic temperature change. But if we go to higher temperatures, so here this is a pulse field measurement at 294 Kelvin, so around the Curie point. You can see here we have a deviation of the pulse field magnetization, so magnetization over field from our static field measurements, because during the pulse we are heating up our sample, and at 60 Tesla we have a huge different temperature of our sample compared to the static field measurements. So you can see here, so during the magnetization pulse, we are heating up and get a different magnetization curve. But we can not only do these simultaneous measurements, we also put some effort in only the pulse field magnetization measurements, some engineering effort. So this is a typical sketch of our pulse field magnetization, where we only measure the magnetization, where we have here our compensated pickup coil system. Here is again our field, external field pickup coils. And there went some effort to have also a fine compensation, to have a extremely high resolution of the magnetization in our sample, to really resolute sharp transitions and features by application of magnetic fields. So this pulse field magnetization preparation is done that you put your samples in such a Kapton tube. You can see here I was able to measure on different types of samples. For example, a powdered sample, which is fixed with some wooden plugs inside these Kapton tubes. I was also able to measure highly air-sensitive single crystals in a sealed glass tube, which you can see here. But I was also able to measure a barred single crystal. But I have to say, in these magnetization measurements, we are not able to measure absolute values in the pulse field. So if you measure magnetization in pulse fields, you always have to stay your results from DC, so from static magnets. Now to go back to simultaneous measurements in the pulse fields. Here I want to present simultaneous measurements of the magnetocaloric effect together with a bidirectional strain. So you can see here the sample preparation, where then this sandwich type sample preparation, and on top of the sample there is a strain gauge glued to measure the length change by application of magnetic fields. So in this strain gauge, you usually measure a change of the resistivity in the strain gauge, and this can be related in the end to a relative length change delta L over L0 of the sample. So you can see here in black, this is the adiabatic temperature change for this nickel manganese indium alloy, where the initial temperature was at 285 Kelvin. As you can see here, we have a negative adiabatic temperature change, so which means we can not only heat up, we can also cool down our samples by application of magnetic fields here, for example, up to 10 Tesla. And then from the up and down speed, we get a certain hysteresis. And quite similar behavior we see in the relative length change in red. So we also have a certain hysteresis by application of magnetic fields in our nickel manganese indium alloy. So now I'm already at the end of my talk, and I want to summarize what I've shown in my talk. So we have to generate highest magnetic fields, we have certain technological challenges, but by overcoming these challenges in our EMFL facilities, we can generate pulsed magnetic fields up to 95 Tesla and static fields up to 38 Tesla. And by applying these high magnetic fields, we can do research on new materials with various techniques, which I've shown, for example, the magnetocaloric effect we can investigate and the magnetization. And these investigations can have a potential application, for example, in cooling devices for the future, where we can try to find new materials to replace, for example, rare earth compounds. And with this, at the end of my talk, I want to thank you for your attention.